Regardless, so a short lecture today, probably, but we still want to talk about alternating series. So an alternating series is a series where the terms alternate between being positive and being negative. And the normal or the most common form, good morning, of an alternating series is something like this. We've got -1 raised to n, or sometimes you see n-1 or n+1. And then we've got some positive term. Good morning. And where we start controls whether the first term in the series is positive or negative. So the terms in this series are alternating. It's either positive, negative, and then on for infinity, or it's negative, positive, and then on for infinity. So, assuming we start with n equals 1, we get an alternating series that starts with a negative term. And if we want to start with a positive term, the most common way to tweak this is to put either a -1 or a +1 in the exponent. And those two things will do exactly the same thing. If we have a +1 in the exponent, now we start with n equals 1. 1 + 1 is 2. So we start with -1 squared. In other words, we start with +1, and then our terms alternate between being positive and being negative. So that's usually all that power up there is. We either have n, or maybe we have n+1 or n-1, and the only thing that power is controlling is the order of the pluses and minuses. And alternating series are usually easy to work with. I was saying, I think this is before you came in, but I was saying this was probably going to be a short lecture, which I don't love. I mean, if you're paying for X credit hours, you get the X credit hours. But on the other hand, there genuinely isn't a whole lot to be said about this topic, because the convergence test is so straightforward. The alternating series test. And the alternating series test is sort of like the anti-nth term test, in that it can only show convergence. So you can never use the alternating series test to show that an alternating series diverges. You can only use it to show that an alternating series converges. And here's what the alternating series test, says. It says that if a series satisfies two conditions, if an alternating series satisfies two conditions, then the alternating series converges. And here are the conditions. First, the terms of the alternating series have to go to 0. Of course, from the nth term test, we know that if they don't go to 0, the series can't converge. The second condition is it's a monotonicity condition, but saying that probably raises more questions than it answers. The second condition says that these terms get smaller as we look at them. We have this chain of inequalities. Let's talk a little, and well, let's first give the punchline, give what this test is saying. If 1 and 2 are satisfied, then the alternating series, so the series that has these terms in it, alternating between positive and negative, converges. So using the alternating series test tends to be pretty straightforward, at least if you don't get too caught in the weeds. I mean, if you try to use the derivative to formally show the second condition is satisfied, that can be kind of a nuisance. But as I say, if you don't kind of get stuck in the weeds, this is usually pretty straightforward. Let's go from 1 to infinity, -1 to the n plus 1 times 1 over n. This is called the alternating harmonic series for reasons that might be kind of obvious. 1 over n is the harmonic series, and that -1 term is causing it to alternate. And again, the only reason, we have an n plus 1 here, because traditionally the alternating series starts with +1 and then alternates like so. And this series converges, and it's using the alternating series test, it's hopefully pretty easy to see this. What do we need to use this test? We need the limit as n goes to infinity of these terms to be 0, which is certainly true. 1 over infinity is 0. So check there. And then we need the series to be what we call monotonic, which is just a multi-syllable way of saying that these terms get smaller and smaller as we go from left to right. And this is a true statement. In general, 1 over n is greater than the next term, 1 over n plus 1. So check, that condition is satisfied as well. And after doing like the ratio test where we had the root test where we had to do all of this complicated algebra and complicated simplification, it can be kind of hard to believe, but that is all there is. These two conditions are satisfied. So this series converges. And that is the alternating series test. Again, the alternating series test can only show convergence. If a series doesn't satisfy the conditions of the alternating series test, it might converge anyway. That's not proof of divergence. Or I guess what I should say, I should walk that back a little. An alternating series that doesn't satisfy the first condition definitely diverges. That's from the nth term test. But an alternating series that fails to satisfy that second condition might converge anyway. And I can give an example, and I guess because this section is so short, I might as well give an example. And this will also let us use a property of absolute convergence. Let's look at the sum from so this is not going to be an alternating series. But let's look at 1 over n factorial, first of all, and we can go from 1 to infinity. So 1 over 1 plus 1 over 2 plus 1 over 3 factorial is 6, plus 1 over 4 factorial is 24, plus 1 over 5 factorial is 120. And I've reached the limit of what I want to try to do in my head. So this series converges. And we've done this as an example before. So I'll just tell you where in your notes it is. This series converges as an application of the ratio test. So this series -1 to the n minus 1 times 1 over n factorial converges. And what's the logic here? I mean, you can use the alternating series test. Let's go ahead and use the alternating series test. As a matter of fact, we just introduced it, so it won't hurt us any to do another example. The alternating series test says that if 1 over n factorial goes to 0, which it does, and you might, well, let me just say that 1 over n factorial does go to 0. I mean, if you look at these terms, it's going to 0 extremely quickly. Like the next term will be 1 over 600 or something. The next term will be 1 over 1,000 something. It's going to 0 quite quickly. And these are, I mean, if we just look at these, 1 is bigger than 1/2, is bigger than 1 over 6, is bigger than 1 over 20, is bigger 24, is bigger than 1 over 120, and so on. Check. So the series converges, and it converges using the alternating series test. So that's another example of the alternating series test, but it's not what I promised you. I said I was going to find an example of a series that doesn't satisfy the conditions and converges anyway. So the sum of the absolute value of -1 to the n plus 1 times 1 over n factorial, this converges. How do I know it converges? Well, because all that the absolute value does is get rid of negative numbers. So this absolute value is getting rid of that -1 to the n. And after it does that, the absolute value isn't doing anything else, and we can scribble it out. And I already made the observation here that this series converges using the ratio test. What does that give us? Well, this tells us that this series converges absolutely. And I know that definitions or theorems that get presented and then don't get used are kind of dust in the wind. We talked about absolute convergence a little before we talked about the ratio test. And we said two things. First, we said that if a series converges absolutely, it converges normally. So the series converges, well, we already decided it converged using the nth term test. So that's not telling us anything new. But the second thing we said about absolute convergence is that you can take the terms of the series and you can move them around, or you can add in parentheses. You can treat them as if this infinite sum is normal addition. And that's a special property. Most series, you can't do that. Grandy's series, which we've talked about, you can't do that. It's only absolute convergence that has this property. So what? Well, let me now (1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial. Doing it so that I don't have to take these factorials in my head. This series converges. It converges via the nth term test. It also converges absolutely. So we can mess around and switch terms and it still converges. So in particular, if we switch the first and the second term, if we just flipped those around, and we flip around the third and the fourth term, and we flip around the fifth and the sixth term, not addition, but minus. And we flip around these terms. We can do that. Absolute convergence says we can do that. So this series converges, and we've generated a convergent series that does not satisfy the conditions of the alternating series test. That second term is smaller than the first term, larger than the first term. The fourth term is larger than the third term. The sixth term is larger than the fifth term. We do not have this string of inequalities that we need for the nth term test to work. Nevertheless, this series does converge. It's absolutely convergent. So it's definitely kind of artificial. I'm not claiming it's not artificial, but here is an example of a series that converges. It's alternating, but the alternating series test fails. In practice, I mean, obviously I had to sort of create this example in a laboratory, right? It's pretty artificial. In basically every situation we're going to look at in this class, if we have an alternating series, it will converge via the alternating series test. Any questions? We have one more piece of material we can cover, and I guess we'd better with 25 minutes left. So let me make an observation. We can use partial sums to approximate to approximate the sums of series. So let's go back. The sum from 1 to infinity of 1 over n factorial. This series converges. We saw it using the ratio test. But what does this series converge to? I mean, I keep using the word convergence. It's kind of a term of art here. What I mean is that this sum exists. We add all these things up and we get a finite number. So it's perfectly rational to ask, okay, so what is this finite number? And we don't know that. Outside of a few special cases, we're never going to really learn to answer that question. It's and that's okay. It's a pretty specialized question. It's less useful than it might seem to be able to answer that. But what we can say is that by definition, this infinite sum is the limit as n goes to infinity of a finite sum. And this suggests a way that we can approximate an infinite sum. We can't go to a calculator or we can't go to a computer. Well, maybe we can, given the march of technology, but we can't necessarily ask a computer to find this limit. But certainly we can ask a computer, so what's the sum from 1 to a billion of 1 over n factorial? Or what's the sum from 1 to a trillion of 1 over n factorial? And those sums where n, capital N, is a very large number ought to be approximating the series. So we're not going to learn ever to find this sum by hand, but let me sit down. Always kind of uncomfortable to be hunched over the keyboard. We can go to a computer and hopefully Wolfram Alpha isn't going to make a fool of me by requiring some kind of a very specialized notation here. But we'll ask Wolfram Alpha, what's the sum from 1 to 1,000 of 1 over n factorial? And Wolfram Alpha will do this for us. It did not make a fool of me, thankfully. And presumably, the bigger this number here gets, the closer this number here is to being the real sum, to being the infinite sum. So we added from 1 to 1,000. Now we can add from 1 to 10,000 or from 1 to 100,000. And the bigger this limit gets, the closer this should be to our answer. And I mean, up to whatever Wolfram alpha is rounding to, up to 1.71828. I don't think this is changing anymore. So we say, okay, 1.71828 is probably pretty much the sum. We haven't managed to find it using any clever math. We just asked our computer to do this sum for us, but it's probably a pretty good approximation. So, in general, there's no formal way of knowing how good such an approximation is. And I use the word formal here because I don't want, I mean, there are definitely limits to technology, but I also don't want to be, neurotic about this or to say things that are, clearly not true. I mean, mathematically speaking, it's completely possible that if I add 2 more zeros here, our approximation will suddenly completely change. Maybe if I add 2 more zeros here, instead of 1.71828, our approximation will suddenly be 2.9 something. And in a mathematical sense, that's true because we have no idea how close this approximation is to our answer. Maybe we're actually not close at all. Well, again, I think it's important to sort of draw distinctions between what's mathematically possible and what's likely. I don't think that when I press the enter key, I'm going to get 2 point something. I very strongly suspect that when I press the enter key, I am once again going to get 1.71828. What I'm actually going to get is Wolfram alpha saying these factorials are too big for us. We can't take them. So let's try to. What do you mean you don't understand my query? Wolfram alpha is weird sometimes. I don't know what to say. Okay, so let's make this big. I mean, everything I said, Wolfram Alpha made a fool of me after all. Let's try making this bigger, but not making it an order of magnitude bigger. Let's go from having a 1 to having a 5. Come on. There. We increased the size of this by a factor of 5. Our suspicions that 1.71828 are a good approximation of the sum, that increasing this wasn't going to change that approximation. All that was true. So again, I put the word formal here because I think sometimes textbooks are math textbooks venture into kind of the realm of the neurotic when they talk about things you can know or things you can't know. Nevertheless, it is true that from a formal point of view, there's no way of knowing how good an approximation is. It's always possible that you think you've got an approximation, a good approximation, but actually you don't. Actually, you're far from the answer. Well, I bring this up now. Why do I bring this up now? If a series converges via the alternating series test, then the finite sum, the approximation. This is an alternating series if it's converging via the alternating series test. So this approximation of the sum is accurate to within A sub n plus 1. Let's make this less inscrutable by doing an example, because this really isn't saying anything hard. It's just, all of this stuff needs an example or two to make it clear. Let's say we're looking at the sum from 1 to infinity, -1 to the n plus 1 times 1 over n factorial. We did this example and we found that it converges via the alternating series test. So let's say that we try to go to Wolfram Alpha and we ask Wolfram Alpha to numerically approximate it for us. Let's ask Wolfram Alpha if it will go from 1 to 100. So our capital N is going to be 100. gram alpha. So from 1 to 100 now, but we've got an alternating series. And what the heck is happening here? What? I have no idea what these diagonal dots are, some kind of mathematical terminology I've never seen before. But here's our decimal approximation, 0.6321 something. What if we went from 100 to 101? Well, we're still at 0.6321 something. Nothing's really changed. In fact, 0.6321, 205588, 20588. This really doesn't seem to be changing at all. And if we go from 1 to 1001, 0.6321, 20588, we're not seeing any differences. So it looks like the sum up to up to 10 decimal places is probably 0.6321, 20588. Well, we can now, using the material on this previous frame, we can make a formal statement about how good this approximation is. It's accurate to within 1/101 factorial. So the alternating series test gives us a bound on how accurate this approximation is. And I mean, 1/101 factorial is an indescribably small number. I mean, I don't know, like, I would not be at all surprised if Wolfram alpha just rounded this to 0. Let's see if it does. So it doesn't, again, we have no idea what this notation is. It doesn't round it to 0, but it does tell us that this is 0 point, and then we have 160 zeros before we have a 1. So like significantly smaller than like if you were measuring molecules or atoms in centimeters or whatever. It's smaller than that. It's an indescribably, or maybe I should say unimaginably small number. So if we want to know what this sum is, we're very happy. We don't have to ask, what if 100 isn't enough? Maybe we should go to 1,000, or maybe we should go to 1,000,000, because in this specific case, we have a concrete bound. If we go up to 100, this is already extremely accurate. Oh, and in spite of what I thought might happen, this was basically a full-length lecture, about 6 minutes early, I guess, but we're done with convergence and divergence tests. It's time to start asking, what do people actually use these series for? And we'll get to that starting next. So get your homework graded. I said within the week, pretty busy week. It will probably be tomorrow, but it will be within the week as promised. There's new homework due on Sunday. And I will see you all Monday. Yeah.